Hello and welcome to this lecture on load paths and tributary areas. This is kind of an exciting lecture for me because this topic is really at the heart of a lot of what structural engineering is all about, and that's really finding load paths. So with that said, what is a load path? And it is just simply, how the loads or demands which are placed on an element get to a reaction. And so what I have drawn here is just a simple beam and columns. And if we expand it out and we look at the free body diagram, we can kind of see quite illustratively that, well, obviously we have some uniformly distributed load on the beam, and then that will turn into a reaction at the ends of the beams. That reaction then has to be transferred as a compression to the columns, and then ultimately as a reaction vertically at the base of the columns. And this load path should be innately familiar to all of us who are watching this lecture, because if we've ever put anything on a table, this is that load path where you might put a dish or your phone or a book on a table. Well, the load from that book has to go across the table, into the table legs, and then into the ground. And so this, load paths is not something which is that new to you, and you might just have never thought about it in these terms before. So that's a very intuitive one because we've used tables. Most of us have used tables for many, many years now. Another topic which is probably quite familiar is trusses. And so if you're taking this course, likely you've already done a statics course. And in statics and with trusses, we've done method of joints. And really, if you think about it, method of joints, in terms of solving this truss, is just a way of working out, well, what is our path of these 3-point loads which are applied to the truss? How does that get distributed through the truss and then ultimately into the reactions? So method of joints is one of those, sort of inherently analytical techniques, which is really around, determining what your load path is. Now, if we're sort of to extend to more cases which are outside of these two, which we should all be familiar with if we're in this class, we really have 3 analytical tools to approach this. The first one is what's called load flow, and it's called load flow because it's analogous to, say, fluid flow, and that's really, for us, just visualizing the path that, a force at a given point on a structure, how does that move through the structure and ultimately get to a reaction? The next step that we could use, or the next analytical tool that we have, is load tracing, and sometimes referred to as load collation. And this is once we already have the load flow worked out, this is our numerical tracking of the force, or the stresses, depending upon what our end goal is with the analysis, through these structural elements. And this is really going to be taking free body diagrams, working out reactions. This is the bookkeeping of structural analysis, where we want to go from element to element and work out not only how does the forces move through there, but what is the quantity of force which moves through a given element to a given reaction. And one of the tools to help with this load tracing is what's called tributary area. And we'll talk about tributary area in a bit more detail here at the end of the lecture. But in a lot of ways, it's really tied back to this load flow and this analogy with water flow in trying to help determine how does a piece of load move from one part of the structure into a reaction. So we'll look at each of those in a bit of detail here in this lecture, and we will start off with load flow. So with load flow, it's, as I said, this visual way to work out how does load get from one part of the structure to the other. So something to note in this picture is the arrows are the path that the force is going. It's not actually the direction of the force. And so if you think about this for a typical gravity system, you can see my cursor up here. We have some point load applied to the beam. Well, it's going to have to go from the beam into the girder, and then from the girder into the column. And, we've got American parlance here, so you can think of this beam as a secondary beam and this girder as a primary beam. And those are effectively talking about the same things, just slightly different terminology. And so this load path is, shouldn't be that different from what we saw at our original table example, where, go from one horizontal element to the horizontal element which supports it, and then finally down to a column into the ground. So we can use these sort of arrows and think of this analogy of, water flow. If you had a drop of water here and these were pipes, it would flow small pipe to big pipe, finally to our sort of discharge pipe here. But, if this sort of, having arrows as the direction is confusing for you, another way you can think about it is doing some qualitative free body diagram. So putting no numbers to this, but, breaking out each piece of the structure, thinking, all right, if we've got some slab here, it's going to be pressing down, and so it's going to have a reaction along the ends, because it's a reaction over the entire distance of the beam. Well, that's going to turn into some distributed load on the beam, and obviously there's a reaction at the end of each beam, which becomes a compression in the column, and that compression in the column ultimately becomes some compression force on our foundation. So doing much the same way as we showed in this last slide, where we're thinking about, well, if we have a piece of load here, how do we go from the slab to the beam to the column to the foundation? But instead of thinking of it in terms of sort of as directional arrows, we're breaking it down into these sort of qualitative free body diagrams. But as I said, doing effectively the same thing, working out what the path of our load is. And if we know the path of the load, we can then sort of work out, well, what types of demands would a given structural element take, and then we can size it appropriately. So I thought, maybe we could just walk through a really quick example. So I have a picture here of the engineering atrium at the University of Auckland, and what I want to walk through is, what is the load path of just the roof structure here in the atrium. So to start off, we always think, well, where's the load going to initiate? And if we think about, well, for a roof, it's going to be the weight of the roof. It might be people walking around on the roof who are doing maintenance. It could also be the rain which is gathering there. But it's all going to sort of happen on the roofing material itself, which could happen at any sort of arbitrary piece, along its whole size. And so the arbitrary piece that we're going to start with for this visualization is going to be this yellow star here. Well, if we're a yellow star, we've got this big open glass bit and can't really get any load in through here. And, for a load path, it's sort of like electricity. It wants to take the lowest energy that it can to get to a reaction, just like electricity wants to take the shortest path that it can, the lowest energy path, to discharge to ground. Again, a very similar analogy here with structures. And so if we have this little star here, what is the lowest path to ground, and what's the shortest distance? Well, the easiest way would be, if we've got purlins spanning this direction, it would be to go out to these secondary beams, which are, timber sheathed. So they're steel beams, but sheathed in timber here. And then that's going to be the same not only for this span, but it's going to happen at each of these spans along the entire roof. So once we've got our load, which has been distributed out to these secondary beams, obviously it has to get, from here to the ground somehow. And we can see, well, there's this big primary beam here, and there's another primary beam here, primary beam on the edge. So that means that the load's going to spread out from the secondary beams out to the ends. And then once we have all of that load applied onto the primary beam, well, we'll spread that load out to the ends to where it's supported. And that support is really on top of these columns. And that means that we'll take that load down to the ground. So all of a sudden, we've worked out what our load path is. It will be from our sheathing and our purlins out to our secondary beams, from our secondary beams to our primary, from the primary to the column here. And by knowing this load path, we can help ensure that we have, a good, competent ability to carry that load all the way through. So we need to make sure that the connections at these primary beams can take the load from the sheathing, not just from the weight of this beam here, and make sure that our connections here at the ends of our primary beams can take all of the load which is generated and coming in from each of these secondary beams into the columns, and make sure that we size the columns to not only take their own weight in the primary beams, but also the weight which is coming in from the secondary beams and from the roofing. And so that should hopefully make some intuitive sense where, as we're moving the load through, we need to make sure that we can account and provide a load path which can support that. And you can think of this again analogous to water flow in a pipe, where if you've got a pipe here, well, you have water moving through each of this. You can't constrict down one end of the pipe that is further downstream, or else it's not going to be able to carry all of that water. So instead of thinking of sizes of pipes, you can think of capacity of the members and the connections which connect those members. So that is, an overview of load flow. And for gravity systems, hopefully it feels very intuitive. And that's because I said, we've most of us have been putting things on tables and shelves and the like for a long, long time. And so we have some sense of how that load has to get supported by the ground and what the load path and the load flow is with that. So, as I said, analogous to load flow, the sort of analytical side of load flow is load tracing, or sometimes referred to as load collation. And with this, we're effectively doing the same thing as load flow, except for we're just putting some actual numbers to it. So we showed this load flow example at the beginning of the lecture. And with this, as I said, the only change here is instead of this being qualitative, it is now quantitative. So we've worked out what this uniformly distributed load is, can solve for the reactions here, and then we know that those reactions will then have to be equal and opposite onto our columns, and the foundation will have to be the reaction which resists that. And so with load tracing, effectively what we do is we go through each step in our load flow. So we work out what our load flow is and what that whole load path is for a little piece of load on top of our structure. How does it get to the ground? And at each of those steps, we just solve, what is the numerical value for what those reactions are. And one of the tools to help aid with that, because if you think, oh, that's a lot of analysis, this is a lot of free body diagrams, a lot of calculations of equilibrium, and you're right. However, as structural engineers and as designers, we like to simplify things because our design is iterative, and because any given analytical step that we might be doing might not be the final estimate for the structure, might not be the final sizing. We might need to go up, and that's going to affect our load. And so effectively, we want to be efficient, and which means we're a little bit lazy. But that little bit lazy is okay as long as we understand the bounds of the simplifications that we're going to use as design tools. And one of these design tools is tributary area. So before I talk about it in terms of structural analysis, I want to talk about how this idea comes about and another analogy. And this analogy, again, will be tied to water. And so the image that I have here is of the catchment area of the Mississippi River in the United States. And if we think of the Mississippi River as analogous to, say, a primary beam in a building, well, we can think, well, if we want to know what our load path is in a building, we also want to know, well, what is our sort of flow path into the Mississippi River. So if, say, a drop of water fell where I grew up here in Ohio, and this is my family's farm here, and that drop of water fell and then it moved into the Little Killbuck, well, the load path or the water path of the Little Killbuck will start here. It'll then go down into the Olentangy River, find its way into the Ohio River, move its way from the Ohio River to the Mississippi, and then eventually down to the Gulf of Mexico. Similarly, if we thought about a drop of rain which falls in New Orleans, it will simply go from New Orleans to the Mississippi River and to the Gulf of Mexico. And if we repeated this exercise throughout this entire catchment, we could eventually draw sort of an area where if a drop of water would fall, it would, eventually run through the Mississippi River on its way to the Gulf of Mexico. And then this is effectively the area where all their tributaries of the river are located, and hence in hydrology we'd call this the catchment area. But we can think of this as this, each of these rivers is a tributary to the Mississippi River, and so this is the area which those tributaries exist in, or as we refer to in structures, the tributary area. And so just like we could have this idea as a, how water is going to move through and eventually get to a given river, we can think of the same thing for structural analysis, how a given load and how much area of a given structure will apply load to a given structure. So let's do a few illustrative examples now that we have that analogy in hand. And one sort of big caveat on this tributary area idea is that it is a big simplifying assumption, and then it only strictly works for simply supported beams, and it only strictly works for uniform loads. However, for some purposes of design, particularly in reductions of live loads, which you'll find out about in a later course, we'll use it for slightly outside of those strict assumptions, but for doing calculations, it must be a simply supported beam for it to hold strictly true. And so to think around, well, how this exists, well, we think about a tributary area. If what we care about for tributary area of each of these reactions, it's effectively going to be, well, what's the load? What's the quickest place for a piece of load to get to the ground? And so for this point load, well, this point load P, its quickest way to the ground is to go over here to reaction 1. This point load P, its quickest way to the ground is to go over here to reaction 2. Similarly, we can think about the uniformly distributed load. Well, obviously, this little piece of load, quickest way is over to reaction 1. And then as we move along the beam, again, we keep going over to reaction 1. But at some point, it will be quicker for this piece of load in a shorter path to go over to the right to reaction 2. And if we plot that up, well, we can see that we have half of the load is tributary to reaction 1, and half the load is tributary to reaction 2 for both of these cases. And so we can use this fact where we've got this very simplified, simply supported beam case, and then we can apply this to three-dimensional structures and help us work out the load path and work out what the load collation needs to be. So we'll work this out with one very simple sort of sheathing and joist example, where up top here, imagine this as a sheet of plywood and these as timber joists. We want to know, work out what the tributary area is for joist 1, joist 2, joist 3, and joist 4. And each of these is spaced some distance s apart, and they are, of course, some length L long. So, as we saw in our previous example, well, we expect that it's going to have to do with sort of simply supported beams. It's going to be roughly half the load is going to go to one reaction, half the load is going to go to the other. So, if we think about our slab, or our piece of plywood here, as our simply supported beam, and you could be looking in this direction, you could see that, well, you've got a reaction here, reaction here, reaction here, reaction here. Well, the first thing that you would say is that, well, this is not simply supported. It's got 1, 2, 3, 4 reactions. And this is one of the simplifying techniques that we have to do, is that we will treat the distance between the joists as its own simple beam. Even though we do have continuity between them for the purposes of calculating deflections and bending moment demands, it's actually a conservative estimate. And so, as I said, we want to approximate and have a tool which will help us iterate quickly in design. So that's the first one, is we assume that between joist 1 and joist 2, that this is effectively a simply supported beam, and we ignore the effect of the span between joist 2 and joist 3, and the span between joist 3 and joist 4. So if that's what we're doing, well, then we can think about this tributary load idea, and we can sort of draw, well, we know that there's going to be sort of half the load's going to go to joist 1 and half the load's going to go to joist 2. And this is a relatively simple, straightforward example, it being a rectangle, but if we're ever confused, what we can do is use this technique of, just like thinking around the Mississippi River, if we put a dot on the map, what is the load path through to the reaction? And if that load path goes through a given river, we say that all of those other rivers are tributary to it. Same thing here. We could put a little dot on our piece of plywood, and we want to know, well, what is the shortest path to the reaction? And if that path goes, say, through joist 1, well, then this dot will be tributary to joist 1 and will be within its tributary area. And because it's, some distance, it's less than S over 2, so less than half the span towards joist 1, and we're spanning the plywood in this direction, well, it's going to go over to joist 1. And we could plot another star, and it could be further away. And again, because its distance is less than half the span, it's going to be tributary to joist 1 because it's a shorter path to get to joist 1. And we could do this for a number of different plots all the way through until we plot something that's, it's actually more than S over 2 away from joist 1. And so it's within S over 2 of joist 2. So it's a shorter path if we're standing here for our load to get to, the reaction on joist 2 by going through joist 2. To get to the ground by going through joist 2. And so it's going to be tributary to joist 2 and not to joist 1. And so if we plotted this up for all points within the span, what we would find is that if we are, within S over 2, so half the span of joist 1, that's our tributary area. And so our tributary area for joist 1 will be S divided by 2 times the length. So that should hopefully look fairly straightforward. And again, we could do this again for another point, and we work out what is sort of outside there. So that's joist 1 on just on one side. What if we look at joist 2? We already know that we've got a couple points coming from this direction. But again, analogous, where we assume that there's a simple support between here and here, and a simple support between here and here. So that's our big simplification and simplifying assumption is that even though we've got this continuous plywood, we assume that it's going to be simply supported between each of these joists. And so if it's simply supported between each of these joists, we know that, for the simple beam, half of that length will be tributary to its closest reaction. And so for joist 2, it's going to be this S over 2, this half the span to the left, as well as half the span to the right, because you can imagine that, there's a little beam here, and there's a little beam here, and the reactions from both of those beams are going to have to go through here onto joist 2. And analogous, because this is a symmetric little structure here, joist 4 will have the same tributary area as joist 1, and joist 3 will have the same tributary area as joist 2. Now that's for our plywood and our joists. Now let's think about our columns, and this is going to be very similar, where we could plot up a little area of something went to joist 2, then it has to come to the reaction of joist 2, and then it has to come into the column. If we're at joist 2 but we're at the further end, well, come to joist 2, over to the reaction, but to a different column. And so again, we can do the same plotting up, and we can find that for this relatively simple structure, so think of this like a table, this column, its tributary area is a quarter of the area of the entire piece of plywood. So it's going to be L1 divided by 2 multiplied by L2 divided by 2. And again, all of this is just coming down to working out what is the quickest path for a piece of load to get into the ground. So those are some general examples. I think that it's always good to have some concrete examples to work with. And so what I want to do is take this example and look at building 405 at the University of Auckland, the engineering building. So it's a steel frame building up at the upper stories, and then the bottom couple of stories have some concrete walls on the exterior. But before we get into the example of doing our tributary areas for these different structural elements, I do think it's important to talk a little bit about the construction, because it will help sort of clear up some ideas around, for our previous examples where we've got plywood and joists. Lots of folks have seen timber framing going up. I think that, the average student really hasn't seen a lot of steel construction, and I want to walk through some of the bits and pieces so that that hopefully avoids some confusion around why we're determining tributary areas that we are. And so with the construction of this building, it's using a composite metal deck and beam system. So the picture here on the right is building 405 under construction, and the picture on the left is of a car park building at a different location, but is using the same general construction process, and I could get a better picture of it. And so what you'll see for building 405 under construction is that we have this metal deck which is running in this direction, and it's running orthogonal to the secondary beams. And then you see down here it's metal deck, and it's got some reinforcing which is stacked up, getting ready to get spread out. And on the other floors, it's concrete. And so the way that these floors are constructed is this metal deck is laid down, and that is used to span in between the secondary beams. So think of this kind of like your plywood sheathing. And then reinforcement is tied on the top, and then it's filled with concrete, as you can see on some of the finished floors here. And so the load path for this is that if you've got a piece of load which is here in the middle, well, it's going to get spread in one way along the deck. So it's going to go parallel to the ribs, because that's the stiff direction. If we were going in the orthogonal direction, it'd be like trying to bend a piece of corrugated cardboard parallel to the corrugations. It really doesn't have any good strength and stiffness there, and so it'll sort of bend into a U. While if you think about trying to bend a piece of corrugated cardboard perpendicular to the corrugations, it's very stiff and very strong. And so it's the same thing here. The load is going to move in one direction, and what we call a one-way slab. And this is typical of steel buildings, of timber buildings, of a lot of concrete buildings. The only time which we might have load moving in two directions really would be for concrete buildings, and you would need some specific reinforcement detailing to ensure that that happens. So, sorry, little brief aside there, but effectively the load path is you're coming down, you're going to move to the secondary beams, and then from the secondary beams you move on to the primary beams, and then from primary beams on the column into the foundation, into the ground. And so, again, to sort of orient yourself before we start looking at the building plan, we have the metal decking, which is running in the north-south direction. So north is over here for the building, running in the north-south direction. You can see here under construction the secondary beams. So those are spaced at even intervals. Then we've got the primary beams, which are running in the same direction as the decking. And so because the corrugations are running in this direction, they don't really have any strength this way, so they don't take any load directly to the primary beams. That all has to go through the secondary first, and then into the columns here. So that's our general load path, which it's quite interesting that we can see that just from a simple picture. We can kind of work out how does this building work from a structural perspective. But I think what's even more informative if we can sort of step through and work out, well, what are the tributary areas for each of these structural elements? And to do that, we'll use the plans of this building. And so this is the sort of entire eastern face of building 405. And we're only going to look in this little sort of corner over here. And this is of the second floor. And so the reason we're doing this is because later in the semester you'll go up and you could go into the MDLS laboratories, and in the wet and dirty space or in the wet and clean space where we'll have an activity later in the semester. The framing is actually, and steel framing is actually exposed, so you can look up and you can see some of this load path for yourself here in the coming weeks. So if we zoom in on that area which we had highlighted, again, a few things to help orient yourself, which to sort of refer back to the photo which we had just seen, as well as show you a few different things now that we're down on the, effectively, this is on the second floor looking down, so if we were on the first floor looking up, we would see the same framing. As you saw in the photos, the floor is spanning in this direction, the roughly north to south. And on these bottom stories, so on the upper stories, there's just columns and primary beams, and then allows you to have lots of nice windows. On these bottom stories, there is a concrete wall which runs along the outside. And that's one of the things that I like about looking at the second story, is that concrete wall will change a little bit around how we interpret these tributary areas. So the first thing that I want to look at is the secondary beams. So these are all of the secondary beams. You can see that they frame into the primary beams or into the walls or directly into the columns. And so what is the tributary area of these? Well, if the floor is spanning in this direction, and then we think about our joist analogy, and then we think about our simply supported beam analogy, you can think of the floor as just a whole bunch of these simply supported beams just stacked up in this direction. So you think about each of the ribs in the corrugated metal deck as a little simply supported beam with reaction here and here. Well, then I've just drawn the tributary area of three arbitrary secondary beams. It's going to be half the span distance and over the entire length. And so if we're a piece of load here, we're going to go into the secondary beam there. If we're a piece of load over here, well, we'd go into the secondary beam over here. We wouldn't go over here. However, little piece of load standing right there, secondary beam, on down to reaction, etc. And the same here. All right, so what about the primary beam? So if we would go through and plot up what the location of, say, the primary beam was, so say we were standing right here, well, we would want to go into the secondary beam and then into the primary. Again, if we're standing here, into secondary beam, into the primary. If we're standing over here, secondary beam, and then we're into the wall. So if we did all of that plotting up for each of the primary beams, we'd get a tributary area that looks like this. And so, again, if we're standing here, go into the secondary beam, into the primary. If we're standing here, into the secondary beam, into the primary. Now, one of the interesting things is, well, if we're standing at this location right here, well, we're going to go into the secondary beam, and we're going to go directly into the column. So we miss the primary beam entirely in these little spans, and that's because, you can think of if we've got our secondary beam tributary area, again, standing here, going in secondary beam directly into the column, we don't touch the primary beam at all, and that's why this tributary area doesn't go the entire length here. You do have to stop and think through, okay, if I'm here, what is my path to the ground? And that's why, anytime you're confused, get a piece of paper out with a plan, and just draw your little X's and work out, well, what's the quickest way through? So those are the primary beam tributary areas. Now let's have a look at the columns. So with the columns, again, we can do the sort of similar task where if we stood here, we're going to secondary beam directly into column. If we stand here, secondary beam into the primary beam, into the column. And we can plot that up, and then we'd get a tributary area that looked like this. Now, the question is, why does this column have a smaller tributary area? So just like with the secondary beams for the primary, if we're standing at this location where the tip of my cursor is, and we move to the secondary beam, well, the next closest path to the ground is to go from the secondary beam directly into the wall, which supports secondary beam. So again, we bypass the column entirely, while if we're standing here, we go to the secondary beam and into the column. So that's our general thing that we need to keep thinking around is, what is the shortest path to the ground? So we can't just arbitrarily take, half the distance. We do have to think through what the load path is. And the last thing I sort of want to bring up on columns is, well, this is the tributary area of the column for just the second floor. We have to remember, though, that columns stack up the building, and so and that path has to go from this area on down. And so, yes, the tributary area for this column here is this area, but then the tributary area for this column here is going to be 1, 2, 3 floors that are above it, and for the column right down at the bottom, it will be this floor plus the floor above plus the floor above plus the floor above plus the floor above. And as each of those stacks up, we have to make sure that the structure can resist all of that load, and make sure that we do have a competent load path and that is strong enough and stiff enough to handle that. So I hope that you found that informative and interesting, because as I said, that's a lot of what structural engineering is about. It's just working around how do we get load from one piece of the structure down to the ground, and what's the path that load is going to take. And so we use load flow as our sort of initial understanding of the structure to help us orient, what is that load path, and so that we can then do our load collation and work out what are the numbers that we need in terms of strength and stiffness and any performance that we have, and we can work out over a tributary area what the demands would be on that structure. And so if we know that the columns have these tributary areas, well, we know that it has to take the weight of the structure in this area as well as any live load that might be applied on here. And then we work that way all the way down to the foundation, and then size our foundation appropriately. And that's the general sense of what structural engineering is. And obviously I've only shown gravity examples here, but it's the same process that we go through if we have wind loading, if we've got earthquake loading, if we have snow loading. So each of those is the same. The orientation of the loading might change, and the load paths might get more complicated for, say, a wind or a seismic load case. But it's the same general process that we do again and again. So with that, I hope you found that informative, and I'd like to say thanks for watching.